1,000 feet long, they reach all the way down into nutrient-rich layers of water. As the buoys rise on the waves above, a column of deep water is pulled up the tubes to the surface to provide a steady diet of ocean fertilizer to turbocharge plankton growth. The pumps could boost ocean life in barren regions, but ultimately, there's an even bigger goal. Vast numbers of ocean pumps could raise levels of plankton so high they'll create immense blooms. These super blooms could capture enough carbon dioxide to take a real bite out of global warming. And when the plankton die, a hefty percentage of them will take the carbon dioxide to the bottom of the ocean.
I'm very optimistic about this. We can make a large array of these pumps and deploy them in the deep ocean, and we've actually wiped out America's carbon dioxide emissions, which is incredible.
Brian believes this system could deep six 1 billion tons of carbon emissions from the atmosphere each year. It's a simple idea, but will it work as advertised? And is it safe? Geoengineering delicate ecosystems like the oceans could lead to unintended consequences. That's why Carl and Letelier have designed this experiment to find out if the pumps pose any possible harm to ocean life. For Brian, the sea trial's a priceless opportunity to see how the big plan will play out on a small scale. And to help him, he's called on the Discovery Channel team. Physicist Basil Singer will check the basic science.
No one has ever made a pump on this scale that's going to the depths that we're sending this one.
Eco-designer Jennifer Langwell will look at design specs and safety.
Basil, did you read that? He's not responding.
And millionaire entrepreneur Kevin O'Leary will analyze the bottom line.
We've got $150,000 floating on its own in the ocean.
Has this ever been done before?
It's never been done. It's never been done. This is going to be a major undertaking to get this pump into the water and then to find out what impact it had on the phytoplankton.
We view this as absolutely essential.
The Discovery Channel team faces a series of challenges. First, they need to analyze the data on plankton populations. Next, they have to double-check designs for the pump valves and long pipes. And offshore, two big questions await them. Will the pumps deploy smoothly in unpredictable seas? And finally, will they work like they're supposed to? While Jen and Kevin begin the planning stage, Basil heads out to sea to confirm the first step in the theory, that nutrient-rich waters from the deep will boost plankton growth.
Okay, here we go.
To find that out, Basil will help deploy this underwater sampling device called a CTD. The CTD is an array of containers designed specifically to collect water samples. It weighs half a ton, and pound for pound, it's one of the most valuable tools in oceanography. The nutrient-rich water lies roughly 1,000 feet below the surface. The job of the CTD is to take several samples from that depth. An onboard computer seals each sampling canister, trapping the cold, fertile water inside.
I got it. Yeah, I got it.
Okay, roger that.
Good job.
Hey.
Good timing.
So these water samples were collected around about 1,000 foot below sea level, and we're going to take them to the lab, and then we're going to do a test to see whether organic matter starts growing in the nutrients that we're bringing up from 1,000 foot.
Absolutely. What we're looking for is these nutrients to stimulate a bloom of phytoplankton.
Basil will see if the nutrient-rich water makes the plankton populations in the samples grow larger. But this is just the start of a 3-month odyssey that takes the team from this colossal seagoing lab to the final experiment in the depths of the Pacific.
The next few episodes focus on my wave-driven upwelling pumps, so let me explain several critical design elements. First, the flexible tube is necessary because it is impractical to deploy many thousands of long pipes in the ocean if they are made from a rigid material like steel or PVC. Second, in normal use, our flexible tube is plenty strong because it sees very little stress. Since it has ocean water both inside and outside, there is very little pressure difference. The tube simply conveys the upwelling water. Third, in our original design, we spool the tube around the buoy so deployment is accomplished in a vertical fashion by dropping the entire unit off the boat and allowing the weight of the valve to unspool the tube, which fills with water as it sinks. This preferred method avoids a situation which you will see shortly, the tube filling with air as it is lying on the ocean surface, then getting blown around by the wind. With our vertical deployment, we also minimize twisting of the tube, which could prevent the water from flowing smoothly up the tube. Finally, for this experiment, we encountered production constraints in fabricating a single 1,000-foot-long tube, so we had to join two 500-foot-long tubes together using a steel coupler. As it turned out, this interim fix caused more problems than it solved, as you'll see in the remainder of the show.
On the research vessel Kilo Moana, the Discovery Channel team and geoengineer Brian von Hertzen joined some of the world's foremost oceanographers for a daring experiment. The oceanographers will test prototypes of ocean pumps at sea. They hope the results will advance a greater long-term goal: to help fight global warming by bringing the ocean's deserts to life. To help test the theory, Basil Singer works with oceanographer Dr. Angel White.
You've got day 3.
So what we're doing today is replicating what the pumps would do in the water, but a controlled lab experiment.
Absolutely. This is a 1-week time series. So what we want to see is the longer they've had to grow, there should be more biomass.
Basil and Dr. White have mixed the deep nutrient-rich water with surface water containing plankton. The mixed samples were left alone for 1 to 6 days.